Welcome to the lecture on network analysis. This lecture is for chapter 7 of our course Operations Research. As you know, a network is a series of interconnected activities of a project which results in some product or services. Network analysis is required for proper planning, scheduling and controlling of project so that the project is completed within the stipulated time and budget, satisfying quality constraints. Several techniques are available to aid project management. However, in this chapter, we will concentrate on two well-known techniques, namely project or program evaluation and review technique, that is PART, and critical path method, that is CPM. The content of this chapter will be covered in 4 modules. So, let us now start our discussion on module 1 of this chapter, that is chapter 7. Let me first define the basic components of a network. A network is a graphical representation of logical sequence of various activities to perform a project objective. So, then first we have to define what we mean by an activity. An activity in the network diagram is a task that consumes time, effort, money or other resources. An activity in a network is represented by an arrow with its head indicating the direction of the project. The figure in the slide shows that the activity Ij, whose starting event is the tail and completion event indicates the head. Predecessor activity, an activity which must be completed before one or more other activities is known as predecessor activity. Successor activity, an activity which starts immediately after one or more other activities is known as successor activity. Concurrent activity, an activity which can be accomplished concurrently is known as a concurrent activity. Dummy activity, an activity which does not consume either any resource and or time is known as a dummy activity. Dummy activity is needed for the following situations: to make activities with common starting and finishing points distinguishable, and to identify and maintain the proper precedence relationship between activities that are not connected by events. Let us consider an example. The diagram shown in the slide, the activity B and C can occur when the activity A is completed. So, B and C activities are independent to occur as soon as the activity A is completed. But if I define an activity D which must start when the activities B and C both completed, then the situation can be dealt with a dummy activity which is shown by the arrow, dotted arrow in the diagram. Nodes, the specific point in time at which an activity begins or ends is called a node. The starting and end points of an activity are described by two nodes, usually known as tail node and head node as shown in the figure. A node is generally represented by a circle, and the numbers within the circle distinguish an activity from another one. Event, this is another name for node, and events can be further classified into 3 categories. When more than one activity comes and joins an event, such an event is called merge event. When more than one activity leaves an event, such event is known as burst event, and an event may be merge and burst at the same time. The merge, burst and burst event are shown in the slide. Fulkerson's rule. This rule is applied to label the events or nodes. First, we should number the starting event by 1. Then delete all rows emerging from all numbered events. This will create at least one new starting event out of the preceding ones. Number then all new events by 2, 3 and so on, and then repeat the previous 2 steps, that is step 2 and step 3, until the end is reached. Activity on node, that is AON network. In an AON network, nodes represent the activities, and the arrows are used to indicate sequencing connection between different activities. So, there is no need of dummy activities, and the diagrams are easy to draw and interpret. Activity on arrow or AOA network. In an AOA network, the activity is represented by arrows, and nodes at the end of arrow state the start and finish of the activity. A convention used in AOA network is to number the nodes sequentially from left to right. A node or event does not consume time or resource. Usually, in the network diagram, we use AOA network. Sequencing. Sequencing means precedence relationship. The first prerequisite of the development of network is to maintain sequencing. In order to draw a network which represents the way the job is to be done, one must have the answers of the following questions. What job or jobs precede each job? We have to know what job or jobs could run concurrently and what job or jobs follow each job. Further, what controls the start and finish of a job or jobs? Now, let me tell the rules for drawing network. There are certain rules we have to follow. First, each activity to be represented by one and only one arrow. Each activity must be identified by its starting and end node. Nodes should be numbered to identify an activity uniquely. Tail node, that is the starting point, should be lower than the head node, that is end point of an activity. Node or event numbered 1 denotes the start of the project, called the initial node, and the node having the highest number denotes the completion of the node or event. Between any pair of nodes, there should be one and only one activity. However, more than one activity can start from and terminate to a node. And arrows should be kept straight, not curved or bent. We have to maintain the logical sequence or interrelationship between activities by the following rules. An event cannot occur until all the incoming activities into it have been completed. And secondly, the dummy activities should only be introduced if it is absolutely needed. Now, we will explain the common errors usually occurred while drawing network. There are mainly three types of error which occur while we draw network. First one is dangling. To disconnect an activity before the completion of all activities in a network diagram is known as dangling. The figure shows that the activity 4, 5 and 6, 7 are disconnected and they are not representing the end of the project. Therefore, this figure shows the error, and this type of error is called dangling error. Looping or cycling. Endless loop in a network is known as the error of looping as shown in the figure. You see that in the figure the activities 4, 6, 6, 7, 7, 5 and 5, 4 forms a loop, and in drawing a network there should not be any loop. That is why this error is called looping or cycling error. Redundancy. Unnecessarily inserting the dummy activity in a network is known as the error of redundancy. You see that in the figure the activity 3, 4 and 4, 5, they are the activities which can occur one by one, but an dummy activity is connected between the nodes 3 and 5, which is actually no need. Therefore, this dummy activity connecting the nodes 3 and 5 is called the redundancy dummy activity, and this type of dummy activity considering is actually the error in the network diagram, which is called the redundancy error. Until now, we have discussed the basic components of network, the rules of drawing a network diagram and the common errors in drawing network diagram. We will now proceed to discuss a very well known method which is called the critical path method or CPM to determine the project duration time and the critical activities of a project. Critical path method was developed by E.I. DuPont Company along with Remington Rand Corporation in 1956-58. The objective of the company was to develop a technique to monitor the maintenance of its chemical plants. Later, this technique has been proved to be useful for developing time cost trade-off for projects that involve activities of repetitive nature. The primary objective of CPM method is to find the critical path, that is the sequence of activities with the longest duration, and to find the float associated with each non-critical activity. An activity in a network diagram is said to be critical if any delay in the activity actually delays the completion of the project. A non-critical activity allows some scheduling slack so that start time of the activity may be delayed within the limits without affecting the completion of the entire project. Before I explain the critical path method, let me introduce some notations. EI denotes the earliest occurrence time of an event I. It is the earliest time at which the event I can occur without affecting the total project time. Li, it is the latest occurrence time of event I at which event I can occur without affecting the total project time. ESIJ means the earliest start time for activity Ij. It is the earliest time at which the activity Ij can start without affecting the total project time. LSIJ, it is the latest start time for activity Ij and by which the activity Ij must start without affecting the total project time. EFIJ, EFIJ is the earliest finish time for activity Ij. It is the earliest possible time at which the activity Ij can be finished without affecting the total project time. LFIJ, it is the latest finish time for activity Ij by which the activity Ij must be completed without delaying the project completion. Critical path method actually considers two types of computation. One is called forward pass computation and another one is called backward pass computation. In forward pass computation, several steps are to be followed. In step 1, set E1 equal to 0, that is the initial node, I equal to 1 is the initial node, and then we set earliest start time for the activity Ij, Eij is equal to the earliest occurrence time of the event I for all activities Ij. Then compute EFIJ which is equal to EXIJ plus TIJ and which is equal to EI plus TIJ. Then move to the next node, say j, where j is greater than I, and compute the earliest occurrence for the node j, that is Ej is equal to maximum over I EFIJ, which is actually maximum over I EI plus TIJ for all immediate predecessor activities. In the next step, if j equal to n, which is the final node, then the earliest finish time for the project, that is the earliest occurrence time for the final node, is given by En is equal to maximum EFIJ, which is equal to maximum of En minus 1 plus Tij. Backward pass computation. In this case, for the latest occurrence of last node n, assume ln equal to En for j equal to n, then set the latest finish time for each activity that ends at node j as LFIJ equal to Lj. Then compute LSIJ equal to LFIJ minus Tij Tij is the activity time. So, we get L Sij equal to Lj minus Tij. Then proceed backward to the node in the sequence that decrease j by 1, and also compute the latest occurrence time of node I, where I is less than j, by using the formula Li equal to minimum of j L Sij, which is equal to minimum over j Lj minus Tij for all immediate successor activities. Now, finally, if j equal to 1, that is the initial node, then L1 can be obtained as L1 equal to a minimum of L Sij, which is nothing but minimum of L2 minus Tij. Based on the above calculations, an activity will be called critical if it satisfies the following conditions: Ei equal to Li, that is earliest occurrence time of the event I equal to latest occurrence time of the event I, and similarly Ej equal to Lj. This is number one condition, and number two condition is Ej minus Ei equal to Tij. Any activity which does not satisfy the above conditions is called non-critical. Now, we will define what we mean by float, total float and free float. First, let me define what we mean by a float. The float of an event is the difference between its latest time Li and its earliest time Ei. Therefore, we can write float is equal to Li minus Ei. It is a measure of how much later than expected a particular event could occur without delaying the completion of the project. Total float. The total float is defined as the amount of time by which an activity can be delayed without delay in the completion of the project. It is the positive difference between the earliest finish time and the latest finish time, or the positive difference between the earliest start time and the latest start time of an activity. Therefore, we can write the total float for the activity Ij, T Fij, which is equal to L Fij minus E Fij, and since E Fij equal to Ei plus Tij, we can write T Fij, that is the total float, is equal to Lj minus Tij minus Ei, which is actually equal to L Sij minus E Sij. Latest start time of the activity Ij minus earliest start time of the activity Ij. Free float. Free float of an activity is the time which can be increased or decreased without changing its immediate successor activities. That is, delaying the activity will not delay the successor event. Therefore, free float for the activity Ij can be computed as F Fij is equal to Ej minus Ei minus Tij, which is equal to minimum of E Sij minus E Fij, where I is less than j. Independent float. If the float neither affects the predecessor activities nor the successor activities, then it is called an independent float. and independent float IFij is given by E Sij minus L Sij minus Tij, which is equal to Ej minus Li minus Tij. Now, we will proceed to see how the critical method can be applied to a network problem to determine the critical path and critical activities of the project as well as the duration of the project. Consider the following network as shown in the slide. Numbers along various activities represent the normal time Tij in days required to finish that activity. So, numbers over arrows denotes the normal times of activities. We have to find the time of completion of the project as well as the critical activities. For this, we first do the forward pass computation. According to the rule, we take E1 equal to 0 and the earliest occurrence time Ej for the event j is given by Ej equal to maximum over I Ei plus Tij, where I is the collection of all events that precede event j. Now, in the figure we see that E2, the event 2, E2 for the event 2 is equal to E1 plus T12, which is equal to 2. Similarly, we can get E3 equal to 2, E4 equal to 2, E5 equal to 6 and E6 is equal to E3 plus T36, that is equal to 5, which is equal to 2 plus 5 equal to 7. Now, for E7 we see that the 3 activities 4-7, 3-7 and 6-7 are merging to the event 7. Therefore, these activities are the immediate predecessor activities. For this, to find the value of E7, we need to consider these 3 activities and then we have to choose the maximum value. So, E7 equal to maximum of E3 plus T37, which is equal to 10, E4 plus T47 equal to 6 and E6 plus T67 is equal to 7, and this gives the maximum value 10. Therefore, E7 equal to 10. Similarly, we can find the value of E8 as 11, E9 as 15, and then straightforwardly we can find E10 equal to E9 plus T9 10. Since E9 equal to 15, therefore, we get E10 equal to 15 plus 4, which is equal to 19. And this shows that E10 equal to 19 shows that the project will be completed in 19 days. Now, we proceed for the backward pass computation. In this case, we set L10 equal to E10 equal to 19, where j equal to n equal to 10. Then the latest occurrence time of event I, where I is less than j, is minimum over j Lj minus Tij. Following this rule, we can straightforwardly calculate L9 equal to L10 minus T910, which is equal to 15, L8 is equal to 12, L7 is equal to 10. And then for the sixth node, we see that we have two successor activities 6, 8 and 6, 7. Therefore, in order to find L6, we need to consider these two successor activities, and we have to choose the minimum value between L8 minus 4 and L7 minus 0, and this gives 8. Therefore, L6 equal to 8. We then find L5 and L4, which are 10 and 6 respectively, and then we calculate L3, L2 and L1, which are 2 and 6 and 0 respectively. When we put these results in the network diagram, we see that the path 1, 3, 7, 9, 10, where EI is equal to LI, that means the earliest occurrence time and latest occurrence times are the same. That is why this path is called the critical path, and the path is shown by the double line arrows, and the other paths except the path 1, 3, 7, 9 and 10, those are called non-critical paths. In this module, we have so far discussed the basic components of network, rules for drawing network, and the critical path method or CPM. We have also taken some example to show how the critical method can be applied to find the critical activities or the critical path of the project and the duration of the project. With this, we end this module.